In the last episode of Bayesian Inference with Stan, our hero Rick faced his toughest challenge yet. His boss had just dropped a bombshell on him. He needed to build a model using Bayesian Inference, and it was due on Monday. But little did Rick know, this was just the beginning of his journey into the mysterious world of probability and Bayesian statistics. As he delved deeper into the world of Bayesian Inference, Rick discovered that it held the power to unlock hidden insights and make accurate predictions like never before. With the help of his trusty friend Stan and a healthy dose of grit, Rick vowed to conquer this formidable foe and emerge victorious. But in this episode, Rick faces his greatest challenge yet. He must build a Bayesian logistic regression model to predict the outcome of a complex sporting event. Can he and his team rise to the occasion and conquer these challenges with their wits and ingenuity? Join Rick and his team as they explore the hidden secrets of data and unlock the true power of Bayesian Inference. The adventure continues in this episode of Bayesian Inference with Stan. Hi everyone, it's been a while, but welcome back to the fourth episode of Bayesian Inference with Stan. In the previous episode, we coded a linear regression to predict match attendance figures, and in this episode, we're going to extend our knowledge by predicting match outcomes. In the first part of the video, as always, I'll outline the data, the process model, and the assumptions that we'll be using for this modeling project. And then we'll focus on writing the Stan program. Again, we'll go line by line and I'll explain each piece of the code as we go and how it relates to the modeling assumptions and the data. Lastly, we'll put it all together and we'll execute our workflow from start to finish. Unlike the last video, we won't compare our analysis to a frequentist result, and instead I'll show you how to run an out-of-sample validation of your model on the new data, which will be very similar to how you might do it in a machine learning context. Once again, we'll be interfacing with Stan through the R programming language using RStudio on a Windows 10 machine. Now, if you don't have the prerequisite background in R, please check out the links in the description. And if you don't want to use R, then Stan interfaces with many other languages like Python, MATLAB, Julia, Stata, but just be aware that the API will be different. You can check out the Stan homepage for support for those languages. And all of the code and data that features on this video, as always, will be available on my GitHub, which you can access in the description box. The data that we'll be using today is the match outcomes from about 1,000 matches of professional men's Australian rules football, each row representing a different match. The Y data in this case will be the outcome of the match, and in this case, the data is encoded as a 1 for a win for the home team and a 0 for a loss for the home team, or in other words, a 0 means a win for the away team. Alongside the Y data, we're going to have 4 covariates, and these will be the current difference in defense rating of the home team and the away team, which is a number between 1 and -1. A more positive number means that the home defense is better than the away defense. The second one will be the current difference in attack rating for the home team and the away team. Again, a number between 1 and -1, and again, a more positive number meaning the home offense is better than the away offense. Thirdly, it's going to be the current difference in ladder position between the home team and the away team between 1 and -1. And again, a more positive number means that the home team has a higher ladder rating than the away team. And finally, we're going to have the difference in the total number of wins in the last 5 matches between the home team and the away team. And this is going to be a measure of the current form line. And again, a more positive number means that the home team has a better form line than the away team. Now let's talk about the process model. Unlike in the previous example in this course, our outcome data are discrete numbers, either a 0 or a 1. They're not continuous values. This means that our chosen process model has to reflect the fact that our output data are discrete numbers. Now, whether your data is continuous or discrete, there are lots and lots of different types of probability distributions you can choose from, and the right one really depends on the context. If Y is a continuous variable, like we saw in the last episode, we often use a normal distribution to describe it because normal distributions are very versatile. But when you have discrete data, or what's otherwise known as categorical data, we can't usually use a normal distribution. We must use a distribution suitable for the discrete events. And again, there are lots to choose from, but a really common one for binary data, that's data that's either between 0 or 1, that's either 0 or 1, we use what's called a Bernoulli distribution. Now I want to talk really briefly about a Bernoulli distribution in the context of Bayesian inference, because it can be a real source of confusion when people go from continuous to discrete outcome space. So recall, if we have a normal distribution, we describe the probability of the outcome of the ith data point as the probability of yi given mu I sigma I is equal to a normal distribution of yi given mu I sigma I. And in this case, mu I and sigma I are the parameters at that point, which are the mean and the variance, and yi is our outcome data of the ith data point. And n has the equation of that describes a normal distribution. And fundamentally, this method doesn't change when we describe binary data, but instead we replace the n, which is the sign of a normal distribution, with a b, which is the sign of a Bernoulli distribution, and we describe the particular probability of y being a particular value given the parameters of a Bernoulli distribution as the probability of y given the parameters is equal to b, or the Bernoulli distribution of y given the parameters. And in this case, y can only be 0 or 1, because that's the implicit assumption when you describe something with a Bernoulli distribution. Unlike a normal distribution, a Bernoulli distribution doesn't have two parameters that describe the mean and the variance. It actually only has one parameter, and we call that alpha, where alpha is a number between 0 and 1. And this can be really weird at first for newcomers. Why don't all distributions have separate parameters that describe the mean and variance? Well, it turns out that actually most distributions don't have two parameters that independently describe the mean and variance. And the normal distribution is a very, very, very special in that regard. It's very normal for probability distributions to have less or more than two parameters. Those parameters don't necessarily have to equal to the mean and the variance of that distribution. So going back to our equation, we have the probability of y given alpha is equal to the Bernoulli distribution of y given alpha. So, just like the normal distribution has an equation, what is the equation for the Bernoulli distribution? Well, the equation for a Bernoulli distribution is alpha to the power of yi, which is the outcome, multiplied by 1 minus alpha to the power of 1 minus yi. So, it's not nearly as complicated as the normal distribution. The other cool thing is that when the outcome is 1, this turns just into alpha. And so when the outcome is 0, this turns into 1 minus alpha. So it's actually quite simple. If your first data point was 0, then its probability distribution would be 1 minus alpha 1. And if the second data point was 1, then its probability distribution would be 1 minus alpha 2. So what's the interpretation of the alpha? Well, alpha can be interpreted as the probability of that particular point being a 1. So, if alpha at the first point was, say, 0.3, we would say that the probability of y1 equaling 1 is 30%. And this doesn't mean that y1 can't be 1, it just means that if we had 100 parallel universes, y1 would only be 1 maybe 30 times out of that 100. So let's go back to our process model. We will describe the outcome data using a Bernoulli distribution. That is, yi is equal to alpha I to the power of yi times by 1 minus alpha I to the power of 1 minus alpha I. And this is all great, but you might be asking, where do the covariates come in? Well, in this case, the covariates will come in by assuming that alpha I is described as a linear combination of the covariates, just like we did in the linear regression example. And that is, alpha I is equal to theta 0 plus theta 1 times by x1 plus theta 2 times by x2, etc. So you might be noticing that one of the differences here between linear regression and Bernoulli regression is that we don't have an additional noise term. And you'd be right, and this is exactly what happens in a Bernoulli regression. The process noise of the model is not specified independently. Instead, it's taken into account by the fact that the probabilities are never exactly 0 or 1. Now, you might also be thinking about a second problem. Alpha I is supposed to represent a probability, and that means it has to be between 0 and 1. But actually, there's nothing stopping this equation of alpha I from going past 1 or below 0. Actually, if you look at it, the range of alpha I is between minus infinity to infinity. So in order for alpha I to only be in the range of 0 to 1, we have to compress the equation using a function that maps minus infinity to between 0 and 1. Now, it turn out to be many, many functions that do this, but a really common function is called the inverse logit function. And the equation for the inverse logit function is 1 divided by 1 plus exponential to the power of minus x. And if you draw this kind of looks like an S-curve. But as you can see, when x gets really, really negative, it approaches 0. And when x gets really, really positive, it approaches 1. So what we do is we put our equation, our linear equation of alpha I, into this inverse logit function. And this will ensure that alpha I is always between 0 and 1, irrespective of what value the coefficients or the covariates are. So now our fully specified process model is that the probability of the outcome y is described by a Bernoulli distribution given a parameter alpha I, and alpha I is going to be described as the inverse logit of a linear combination of the covariates and the coefficients. Finally, let's discuss the priors that we're going to use. We have 5 parameters, so we've got the intercept and 4 covariates, and so we're going to need 5 priors. I don't really know much about the problem, so I'm just going to put a normal 0-10 prior onto every parameter. And this is going to ensure that we're being ignorant about the sign of the effect and that we allow for order 10 away from the center being plausible. In essence, we haven't really introduced anything specific in terms of our prior knowledge, other than saying that we don't expect any parameter to be particularly positive or particularly negative. Now we're ready to write the stand program that defines the equation of our posterior in terms of our unknown parameters and the data. Just like in the previous video, we're going to start with 3 empty blocks. They're going to be the data block, the parameters block, and the model block. In the data block, n is going to be the number of observations we expect, while c will be the number of predictor variables in the data. We'll also declare another variable called xtrain, and that's going to be the matrix of training data, which is going to be of size n by c. Finally, the match outcomes will be our outcome data, which in this case is binary. Therefore, we're going to declare that we expect the data to be either 0 or 1. Next, we'll declare our unknown parameters. In this case, we'll have 2 types of parameters. The first will be the coefficients, and this will be a vector of length 4, 1 coefficient for each covariate. The next will be a single floating point number, denoted with the type real, corresponding to the intercept term. As pointed out before, logistic regressions do not include an explicit term for process noise, so there's no need to estimate a sigma parameter in this project. Also, for each of our parameters, we do not need to specify any bounds, because they could be any sign. So, we've pretty much specified all the parameters, and we can now move on to the model block. As a reminder, the model block is where we define the equation of the joint posterior probability distribution as a function of both the parameter and the data variables. And to be clear, these variables come from the declarations we made in the previous 2 blocks. Anything we haven't declared in those blocks won't be recognized by STAN. Similar to the previous episode, let's start with specifying the prior. I'm going to specify the prior for both the coefficients and the intercept term to be a normal with 0 mean and a standard deviation of 10. And I can write this using the tilde notation, where I will absolutely not forget to remember the semicolons. Now, when the model compiles, each sub-equation that I define in the model block is specified internally, and then all multiplied together to form the expression of the posterior. At the moment, we've only specified the prior equations, so currently our posterior simply looks like the multiplication of all of the priors. To complete our posterior, we need to add the likelihood expression, which also occurs inside of the model block. Recall that our process model says that we will assume each outcome comes from a Bernoulli distribution of probabilities, where each probability is given by the inverse logit of the linear combination of the predictor variables plus an intercept term. If we imagine the coefficients as forming a column vector and the predictor variables as our matrix, then we can write this compactly in a vector product form like so. And in STAN, the syntax for the likelihood mirrors this equation. So we can write match outcome tilde Bernoulli, inverse logit, which is a function inside of STAN, and inside of that we say x times by the coefficients plus the intercept term. Now that we've fully specified the entire posterior, we've actually fully specified the entire STAN code. If we compiled this, it would absolutely work and it would give great results. But just like in the previous video, there are always ways to optimize and improve what we've written. At this point, it's time to introduce another block type, and this is called the transformed parameters block. This block goes between the parameter and the model block, and essentially, as its name suggests, is for parameters that are functions or transformations of other parameters but do not contain any randomness. The transformed parameters block is really useful when you have a derived quantity that's interesting, but it's not directly estimated by the model. Variables in the transformed parameters block cannot be easily given a prior, and you cannot assign them new values, and their inference is purely based on the inference of parameters inside of the parameters block. In our code, a good candidate for the transform parameters block will be the expression inside of the Bernoulli sampling statement. We can define a new intermediate variable called yprob. We assign it deterministically and make it equal to the inverse logic calculation. Yprob will now be the derived outcome probability of each match. Once we've defined it, it becomes available for us to use in the model block. Now that we've written our stand code, it's time to jump into RStudio and execute the workflow. The packages that we'll need, as always, are dplyr for data wrangling, ggplot2 for graphs, and rstan as the interface for using rstan with R. I've got a tutorial on how to install and set up rstan on YouTube, so make sure to check it out if you're having trouble. Now that we've got our packages loaded, we load the data into the environment from a CSV. What we will also do is split our data into a training dataset and a test dataset. The training dataset will be all the matches before 2019, and the test will be matches during 2019. Later on, we're going to use the test dataset to see how accurate our model is on data we've never seen before. We'll then compile the stand program we just wrote using the function stand_model from the rstan package. This will take as input the stand program file location and output an executable object that you can sample from. This step can take up to 1 to 2 minutes. The next step is to sample from the stand model object to create the joint posterior table. This will first require us to prepare training data to pass to our executable. In R, stand accepts the data as a list, so we must create an empty list and populate the elements of the list with the specific names and types that were declared when we wrote the stand code. In our example, the declared data are an integer for the number of data rows n, another integer for the number of covariates c, and a vector for the outcome data, match outcomes, and a matrix of covariate data, xtrain. Now that we've prepared the data, we're ready to sample, and we use the sampling function, setting the number of chains to be 2 and the number of iterations to be 2000. If you're wondering what these parameters are, be sure to check out episode 3, where I go into detail about what the number of chains and what the number of iterations actually means when it comes to sampling. Once we press sample, we can see the summary of the progress printed to the console. Now that stand's finished, let's look at the results. The joint posterior table is extracted using the extract function, and here we can see the individual samples of each model realization. A summarized version of the joint posterior table is calculated using the summary function, and you can see this table shows the mean, the standard deviation, and the various quantiles that define the distributions. As always, before we look at the results in more detail, we have to check that the sampling has worked. From the summary table, it looks like all the r-hats are less than 1.05, which is a great sign. Also, it looks like the number of effective samples for all parameters are greater than 150, which is another good sign pointing to unbiased sampling. If we check the number of divergent transitions, you can see that for each chain, it's 0, which is the strongest evidence yet of good sampling. Now, other than the quantitative metrics above, qualitative measures of sampling are also quite popular when diagnosing the quality of sampling. The most popular qualitative test of good sampling is called the pairs plot method. This is a method where we plot the posterior samples of each pair of parameters, which we can invoke using the pairs function. Each point in this plot is a model realization. So for example, this point is where coefficient 1 was minus 2.5 and coefficient 2 was minus 0.5. What we're really looking for in the pairs plot is a nice random blotch of points. If there's any suspiciously systematic patterns in the pairs plot, this can point to the sampler having bias in its sampling strategy. Here are some examples of other models where the sampling looks very suspicious. In our example, we see we've got a little bit of correlation in the posterior here, but nothing points to anything suspicious going on. So, with all of the evidence, I think we can safely assume that the sampling has worked very, very well. So, now that we are certain our sampling is converged, let's interrogate the results. First, let's look at the marginal distribution of the intercept parameter from the joint posterior table from Stan. Remember, all we need to do is isolate that column in the posterior table and draw its histogram. For this, we'll use ggplot, and we can see that the distribution is between 0.1 to 0.6. This means that every value in this range is a plausible value of the intercept after seeing the data, with the most plausible values ranging from 0.2 to 0.5. But what's the interpretation of this level of intercept? Well, to understand this, let's go back to our process model. Our process model says that the probability of a particular outcome of the match is the inverse logit of the linear combination of the predictors and the coefficients plus this intercept term. Now let's do a little bit of rearranging. The equation also means that the logit of the outcome probability is equal to the linear combination of the predictor times the coefficients plus this intercept term. And if you work through all of the math, the term on the left-hand side is the log of the outcome probability divided by 1 minus the outcome probability. This expression inside of the log is also called the odds ratio, and it's a much more common term to hear when describing the outcomes of events. For example, your friend might describe the outcome of a particular match as being 3 to 1 chances of winning, and that is what we mean by an odds ratio. So we can see that the intercept term is actually related to the odds ratio. If we do a little bit more math and take each side as the exponent to the exponential function, we can see that the intercept term is a multiplication factor of the odds ratio. So if our intercept term is, say, 0.3, then e to the power of 0.3 is 1.34. This means that the effect of the intercept term is to increase the odds ratio of the home team winning by 34% over the baseline. So the intercept term is really another way of describing the home ground advantage. Now let's go back to our code. We can do the same thing with the coefficient parameters. Rather than draw a histogram for each parameter, I'm going to draw a line segment representing the 95% credible interval. And that's a line going from the 2.5th percentile to the 97.5th percentile. I'll draw this line segment for each one of the coefficients and order them in descending order. We can clearly see the effect size of each variable. Having a superior offense, defense, and ladder position is associated with greater chances of winning. However, and this might come as a surprise, the team's form line is not really associated with greater chances of winning. Okay, so I've now shown you how to look at the coefficients and interpret their meaning, but isn't the whole point of this model to predict outcomes of future matches? So how can we use our model to predict matches that we've never seen before in the test set? Well, one way we could do this is to use the simulation technique that we've talked about in episode 2 and as an exercise in episode 3. This is where we take each realization of the coefficients and the intercepts and predict the outcomes of the matches. Now, we can do this in R, and I encourage you to give it a go, but there's actually a way to do it in Stan, and in this case, we're going to have to modify our Stan code to accept a test set. So let's go back to our Stan code and add some more variables in the data block. I'm going to add the number of test set data points, n-test, and the X matrix for the test set, x-test. Now what I'm going to do is introduce you to another modeling block in Stan. This block goes after the model block, and it's called the generated quantities block. This generated quantities block is used to run posterior simulations in Stan, or in other words, it's used to generate new posterior quantities. Now I want to stress here, you don't need to use the generated quantities block. Everything you do in the generated quantities block could be replicated outside of Stan, just using the joint posterior probability table. But the generated quantities block is very useful because it simplifies a lot of the code you need to run posterior simulations, and it's probably a bit faster because it's compiled to C code. So first I'm going to declare a new variable, ypred_test, as a real container of length n-test. Then I'm going to loop through each of the out-of-sample points and calculate the outcome probability. This is simply the inverse logit function of the X matrix of that particular row multiplied by the coefficients plus the intercept term. The generated quantities block gets run after the inference of the parameters, so you can really think of this as that we're using the inferred coefficients and intercept term to run new posterior simulations. Now let's go back to R. We have to run the entire code again, and we need to make a few modifications to the input data to accept the test set. We'll run that from top to bottom, and as you can see, it runs just fine. All the posterior results are the same, but now we can see that in our results object, we have access to the results of ypred_test. Each ypred_test has a distribution associated with it, and we can see that from the summary table. What I'll do now is plot the range of predicted probabilities of each of the test set matches in order from most likely to least likely, and we can also color the points based on the actual outcome of that match. So we can see that these points are colored blue and these points are colored red, and those which are colored blue tend to have probabilities of a home win greater than 50%, and vice versa for those colored red, and that's exactly what you'd expect for some kind of probabilistic classifier. And finally, we can predict the range of out-of-sample accuracies for our model. We can do this by extracting all the realizations of outcome probabilities for the matches, and then compare them with the actual outcome, assuming a cutoff probability of around 50%. The model has an out-of-sample accuracy ranging between 58 to 64%, which is not bad, but not that great either. But considering that we have only got 4 different predictors, that's pretty good. Now for this episode, I will leave you with 2 exercises. The first is going to be to manually calculate the out-of-sample probability of winning and compare that with the one calculated using the generated quantities block. Now keep in mind they should be exactly the same. And then the final exercise will be to calculate the range of the rock area under the curve metric for our classifier. And again, this should be a range of numbers based on the range of predicted probabilities. We're now at the end of the 4th episode of this course. In the next episode, we'll switch football codes and move on to predicting the margin for soccer matches. And this is where we'll need to use a more interesting likelihood function, other than a normal or a Bernoulli distribution, in order to better represent the data generating process. As always, if you have any questions, feel free to post them in the comments below, and I'll try my best to get to each of them. If you liked the video, give it a thumbs up, subscribe, and turn on the notifications bell, and I'll see you in the next episode.